Hi everyone, and welcome to the short video about sets, operations and relations. In this video we are going to learn what sets are, how to formally write sets, how to calculate and operate with sets, and finally we will have a look at different relations sets can have. What is a set? A set can be understood as a collection of unique elements, meaning that each element is different from the other elements. Formally, sets are written with curly parentheses. So you have the parentheses and inside of them you have the elements that are inside of this particular set. When dealing with sets, one usually writes them with capital letters, while the elements of the set are usually denoted with small letters. These are already the basic building blocks for sets. Now onto some properties of sets and important facts. Sets are not ordered, which means it does not matter at which location inside the parentheses an element is located. As long as it is inside of the curly parentheses, it is an element of the set, regardless of its position. This means that the sets here, AB and BA, are the same. They contain the exact same elements and the order of writing them is not important. Next on, if we want to say that X is an element of the set A, we write XEA, so this E stands for element. This is a very important sign that you will see quite often in mathematics. You could also say that X belongs to A or is a member of A. For expressing the opposite, namely that X is not an element of the set A, we use the same sign but cross it out. So this means here that X is not an element of A. Furthermore, it is important to know that the size of a set is not limited. There can be a finite number of elements, but there can also be infinitely many elements in a set. The type of the things that are inside of a set is moreover not bound to numbers. A set can contain any type of element, so things like letters or functions can be elements of a set. Even sets can be elements of another set. The last thing I want to mention here is that a set is not bound to one element type, meaning that they can be mixed. In this example here you see a valid set that contains a number, an apple, a function f of x, a flower, and a set, which again contains letters. So now that you have learned the most important facts about sets, we will have a look at different ways of how to denote sets. There are two different methods for describing a set, namely the listing method and the rule method. The listing method just means that you simply list the elements of a set. This is done inside the curly parentheses and the elements are separated by commas. Here you see two examples. S1 describes the set of all digits, so you write the digits separated with commas inside the curly parentheses. Here you should remember that the order of the digits is not important, as we've learned before. Writing them in a different order would still describe the exact same set. The second example, set S2, has the English vowels as its elements. This is a very basic and intuitive way of how to write sets. But what happens when we have a set with a large amount of elements? You surely don't want to write down each single element. This is precisely where the rule method comes in handy. Here the set is described by a rule which defines all the set elements inside the curly parentheses. You now write a variable for the elements in the side of the parentheses, and then after a colon or straight dash we write the condition for it. Looking at the examples, S1 and S2 describe the exact same sets as above. So now that you know what a set is and what it looks like, let's move on to some important definitions. As already stated earlier, a set can contain either finitely or infinitely many elements. A set that contains a finite number of elements is therefore called a finite set. Note that a set with no elements is also a finite set. A set with infinitely many elements is then of course called an infinite set. One concept that is very important is the cardinality of a set. While this word sounds a lot more complicated, it actually just stands for the number of elements a set has. In this example we have the set 157. As it contains 3 elements, the 1, the 5 and the 7, it has a cardinality of 3. The cardinality is denoted with these vertical straight lines. As stated on the last slide, a set can also contain no element at all. This set has a special name, the empty set. We write it with curly parentheses without anything between them, or with this other sign that looks like a 0 or an O with a diagonal line. Another word that you might encounter is the singleton set. A singleton set is a set that contains exactly one element, no more, no less. Now let's move on to set operations. As sets are mathematical objects, we somehow want to operate with them. Possible set operations are uniting two sets, intersecting them, taking the difference, and calculating the Cartesian product. The four operations I just named are all between two sets and will always result in a set. The union of two sets A and B, denoted by a U-shaped sign, is the set of all elements that are either in A or in B or in both. So this means we take all of them and put them together in one set. The intersection of two sets A and B is the set of all elements that are both in A and in B. This means that we only take the elements that are members of both sets. Formally, this is written like the union, but upside down. The complement of a set A is the set of all elements that are not members of A. This often needs some context, because otherwise the resulting complement is infinitely large. So the complement always refers to a context in which we know all possible elements, for example, all digits. If A would then contain, let's say, the 0, 1, 2, and 3, the complement would be a set consisting of the 4, 5, 6, 7, 8, and 9. The complement is usually denoted with a small c, written like an exponent. The same idea of complementing can also be applied to two sets. We want to have all elements from a set A, but delete the ones that are also part of another set B. This is called the difference or relative complement and is denoted by a diagonal line. The last set operation here is the Cartesian product, denoted by an x. The Cartesian product is the set of all possible ordered tuples AB, with A coming from set A and B coming from set B. The important thing here is that tuples are ordered, while the set, as every set, does not care for orders. Here I want to show you some examples for the previously explained set operations. The union of the set 1, 2, 3 and 4, 5 is the set containing 1, 2, 3, 4 and 5. In the second example, remember that the elements of a set are unique, so no elements appear twice. Therefore, doubled elements will still only appear once in the result. For the intersection, we only keep the elements that are part of both sets, which are the 2 and the 3 in this case. For the difference or relative complement, we simply look at each element of the first set and check whether it's also an element of the second set. Only if this is the case, we add this element to the resulting set. In the example case, the 1 only appears in the first set, while the 2 and the 3 are also elements of the second set. The 4 is not important here because it's not part of the first set. For the Cartesian product, you simply need to write down all possible tuples with the first element from the first set and the second element from the second set. If you want to, you can pause the video here and try to really understand the results. Now I want to move on to relations between sets. Relations here means that we somehow want to compare two sets and want to be able to write specific relations easily down in formulas. First of all, sets can be equal. This is the case if they contain the exact same elements, so every element that is part of set A is also part of set B and vice versa. Then and only then A and B are equal. Equivalent, on the other hand, means that the two sets have the same cardinality. As a reminder, cardinality refers to the amount of elements a set has. Here are some examples of equal and equivalent sets. For the equal sets, remember that the order of the elements doesn't matter. Therefore, in the second example, the two sets are still equal. Now to the equivalent sets. The first example is the one you saw from the equal sets. It is also equivalent because the cardinality is the same. Both sets contain 3 elements. In the other two examples, you can see that we really only care about the amount of elements, no matter what the elements actually are. One interesting thing to mention is that equal sets are always also equivalent. For being equal, they have to have the exact same elements, which again means that they of course also have the same amount of elements. But be careful, this does not work the other way around. Equivalent sets are not necessarily equal. Look at the example at the second and third example for equivalent sets. They are equivalent because they have the same cardinality, but they are not equal as their elements are different. Of course, there can also be other relations between two sets. Like all relations, they have their own notations. The notations you see here are very fundamental and therefore important to remember. First of all, let's take a look at the subset. A is a subset of B if every element contained in A is also contained in B. So A is a smaller or equal set that is fully contained in B. A proper subset is a special subset. If A is a proper subset of B, every element from A is also an element from B, but there also have to be elements in B that are not elements from A. So this does not contain the case that the sets are equal. Superset and proper superset are basically the same concepts, but the other way around. If A is a subset of B, then B is called the superset of A. The same then also holds for the proper superset. Here are some examples for subset and proper subset. You can see the same three examples for both, but in the last case we don't have a proper subset, therefore it is crossed out. It is not a proper subset because the two sets are equal. The other two cases are indeed proper subsets. Each element of the first set is part of the second set, and the second set additionally contains other elements. The last two concepts I want to talk about in this video are power set and disjoint sets. The power set, denoted as P of A, is the set consisting out of all subsets of A. Here it comes in handy that we just learned what a subset is. Disjoint sets are sets that don't have any common elements. This means that their intersection results in the empty set. Here I have some examples for you. The power set F1, 2 is the set that contains the empty set, a set that only contains a 1, the set that only consists of a 2, and the set containing the 1 and the 2. So we just need to list all possible subsets. Here you should never forget the empty set, as it is always a subset. The second example is basically the same but with 3 elements. For the disjoint sets, you can clearly see that in the first examples, the two sets are disjoint. They don't share any common elements. However, in the second examples, the sets share a common element, namely the C, and therefore they are not disjoint. Alright, that's it for this video about sets, operations, and relations. By now you should have an idea of what a set is, what it looks like, what union, intersection, complement, difference, and Cartesian product are, and how sets can be related. I hope you enjoyed it and see you again in the next video about numbers.